Section 2.5 talks about the precise definition of a limit. We did limits back in the days, and I just want to remind you really quick how this works. So the idea is, if I'm looking at a graph and I picked x equal a, if the y value is this number L, then when I take the limit as x approaches a of y equal f of x, I'll get this L. Kind of like when we did the shortcut for this problem, how do you find the limit? Plug 2 in, 2 squared, that's 4, times 2, that's 8, minus 1 is 7. That's using the shortcut. But before the shortcut, what we did, we picked values for x. So we're taking the limit as x approaches 2, let's say. We picked, when you could pick above or below, it doesn't matter. Let's say we're going to approach this from the left. So when I said pick the first value, we started back in the days with 1.9. Now if you notice, by picking 1.9, you are 0.1 away from the actual value. And we use the calculator. Let's do the same thing. So if I take the calculator and throw 1.9 twice the answer squared minus 1. I'm getting an answer of 6.22. Now we know it's 6.22, so when I went, let's say the idea was this is 2, and let's say this is the 7. By picking a value below, so if this is 2, let's say that's 1.9, the answer was 6.22. I'm far from 7. So what I did, the second round, we said, okay, let's pick a closer number. How about 1.99? How about if I got closer? Now, shouldn't you expect the y to be closer to 7? And if I take that and I plug in 1.99 and b call it, my answer is 6.9. What was that? 6.9202. So I noticed that, look, I got closer to 7. What if I wanted to pick a value of 1.999? I'm getting even closer. So if this is A, first I picked, this is 2, I picked 1.9, then 1.99, then 1.999. What would happen then? So if you remember, the goal is to get the y value to match to as many decimals as we need. I recall the function 6.992002. Now I notice that this value came closer, but here I could see I locked it in at 1 decimal place. Now it's accurate to 2 decimal places. What if I went ahead and I threw a 1.9999? So again, I'm going to summarize all of this for you. 1.9999, we call the function. The answer is 6.999. So I notice now this is accurate to 2 decimal places. So the idea was, let's say I'm enlarging this greatly. And let's say this is 2. First I picked, let's say this is 1.9. I got an answer of 6. I picked 1.99. I get an answer of 6.9. Now I know it's 6 point some. I picked 1.999 and I got the y values to be from 6.9 to 6.99. I picked 1.9999 and I get the value to be 6.999. So now it's accurate to 2 decimal places. I'm guessing, just a guess, if I picked 1.9999, this y value will be 6.9999 and more numbers, and now it's accurate to 3 decimals. The idea is to get those y values as close as possible, and then if I round them, I'll know it's a 7 by picking numbers as close to 2 as I like. Of course, I could have went from the right. So let's see how this definition plays. It says, let f of x be defined for all x except at a. So we're never going to use 2 in there, right? We always use 1.9999 or 2.001 over an open interval containing a. So around a, right? Above or below. Let the real number, let L be a real number. Let's say in our example, that's the 7. Then the limit as x approaches 2 of f of x, which is 2x squared minus 2x squared minus 1 is 7. Now, the definition goes, if for every epsilon bigger than 0, there exists a delta bigger than 0, such that whenever I choose the value for x to be the difference between that and the actual a, remember a is 2. So when I picked 1.9 minus 2, I got 0.1. When I picked 1.99 minus 2 in absolute value, that's 0.01. So that was 0.1 away from 2. This was 0.01 away from 2. This would be 0.001. That's why we're talking about the control. I can control x and what delta is. What's delta? A very small number. Then the difference between f of x and L is smaller than epsilon. So if I wanted to really mark those, that's the epsilon they're talking about, and that's the delta they're talking about. Notice that if I take 7, and that will be 7 plus epsilon, and this will be 7 minus epsilon, or the absolute value of f of x minus L, y, which is 7 minus these numbers, is a very small number. And I got that by choosing values very close to 2. I could choose it at both ends. Say that is 2 plus delta and 2 minus delta. 2 minus delta meaning I'm picking points below the 2, and I could pick points above. So recapping this definition one more time. Now I colored it. Let me write it on. There are symbols for those. If you really want to see it, let me show you how it works. You could use that. So this is the precise definition of a limit. It says, so we're going to start with given epsilon is bigger than 0. So you tell me, how close do you want these numbers to be? You want it to be accurate to 5 decimal places? What's epsilon? A very small number. That's the difference between 7 minus 6.22. In the beginning, that was 0.78. Then here, it was 7 minus 6.9202. Now, I know that's accurate to 0.01, then 0.001. These are the epsilons, the very small numbers. There exists, the symbol for there exists, backwards E. A delta, what's delta? Delta is these numbers between 2 and 1.99 that I'm choosing, such that you could denote with backwards belongs. Of course, you don't have to use it. You could read the words. You could say, given epsilon is bigger than 0, comma, there exists a delta bigger than 0, such that if or whenever this is true, then you have to show this. So you're going to make all of this assumption. You're going to assume all of these things with one minor change. So we're going to make all of this assumption with one minor change. We need to figure out what that equals. And we have to show this. So if I want to write this as we did up there, we're going to say given as the definition states, given epsilon is bigger than 0, there exists a delta bigger than 0, such that whenever 0 is less than x minus a, that's the limit right there, the difference of those, is less than delta, we have, and you're supposed to show this. absolute value of f of x minus n should be less than epsilon. Of course, you are welcome to say, given epsilon is bigger than 0, there exists a delta bigger than 0 such that whenever 0 is less than x minus a less than delta, we have absolute value of f of x minus n is less than epsilon. So again, there exists, that's a symbol for it, such that there exists, okay, yeah, that's right. Did I leave anything out? There exists a delta bigger than 0 such that whenever, yeah, that's it. Okay, and here if I wanted to do this, the same deal, I would say, well, given epsilon bigger than 0, there exists a delta bigger than 0 such that whenever x minus c in this case is less than delta, we have absolute value of the difference of those being less than epsilon. And that's really how you word the problem. Now let's go into the actual work. There's a small minor step that you need to do, and let's get that out of the way. We're going to start every problem in this section the same way. Given epsilon is bigger than 0, there exists a delta bigger than 0 such that whenever whenever x minus 2 in this case is less than delta, which equals, we leave space, we have the absolute value of the difference of those. Now this is the deal. You need to get an x minus 2 out of that. That is 5x minus 10. If I factor a 5 out, now if I factor a 5, if I factor a 5 out, now isn't x minus 2 less than delta? So I could say this is less than 5 times delta. Remember, I want, for this to work, I must get an epsilon. So, since I got a delta, what must I set delta equal so that I'll get an epsilon in the next step? Shouldn't I set delta to equal epsilon over 5? This way I'll take epsilon over 5, the 5's cancel out and I get an epsilon. Therefore, the limit as x approaches 2 of 5x plus 8 equals 18. That's pretty much what you have to do. There are two cases. This is the first case. Let's look at this problem. Given epsilon is bigger than 0, there exists a delta bigger than 0 such that whenever okay, why am I having a hard time writing whenever, man? Whenever 0 is less than x minus 10 is less than delta, which equal, we have absolute value of the difference of those. minus a negative 5 is plus 5. Now I need to get x minus 10 out of this. That will be an absolute value of 8 minus 4x over 5. If I get a common denominator, that's 40 minus 4x over 5. Factor out a 4 over 5. Wouldn't that be x minus 10? Now, can't I say this is less than or equal to 4 over 5? And isn't this less than delta? Or delta is bigger than that? So here again, the same game. If I want an epsilon at the end, what should I let delta equal? So if 4/5 delta equal epsilon, then isn't delta 5 epsilon over 4? I could choose this to be whatever I want. If that's what it is, I'm going to put it right there. And I'll get an epsilon, and therefore the limit as x approaches 10 of 3 minus 4/5 x equals a negative 5. Now, of course, you erase all of that, and everybody's happy. Or you could just, out of mind, you just put it on the side, and there it is. Okay, let's look at the next problem. We're going to take the limit as x approaches to show proved. So we start with given epsilon is bigger than 0, there exists a delta bigger than 0 such that whenever x minus 2 is less than delta, we have absolute value, and this is kind of a big mess. Now here I could factor that. I believe that factors into 2x and x minus 2 and a plus 1. That's 2x minus 4. So that's pretty good. Why? Because I just want to get an x minus 2 in there, so I could replace it by something bigger. If I factor a 2 out, that is less than 2 times delta. So what do you think I should let delta equal? What should I put there? Well, obviously epsilon over 2. If I put an epsilon over 2, those cancel out. I'll get an epsilon. Therefore, the limit as x approaches 2 of 2x squared minus 3x minus 2 divided by x minus 2 equal a 5. This should be the final conclusion. All right, now this is working properly because I'm off by just a number, and I could figure out what the number is. So on the first problem, we had a 5. We divided by 5. We have multiplied by 4/5. To get rid of that, we multiply by 5/4. And here we had 2 epsilon. We divide epsilon by 2. But sometimes that's not that simple. And here's a problem. Given epsilon is bigger than 0, there exists a delta bigger than 0 such that whenever zero is less than x, oh, it's a lot of 2, it's just a coincidence. Here I'll take x squared plus 2x minus 8, the difference of those two. And I notice that's x minus 2 into x plus 4. Now I know for a fact that this is less than delta times x plus 4. We have a problem. This is not a number. I could let delta be a number, a small number. If this happens, you go on the side, you say, look, I can only control x minus 2. it should be less than a small number. I'm going to choose 1. We always choose 1 for a reason, because if you choose a decimal, if you use 0.0001, the numbers become tedious. Choose 1 always. That's allowed, even though 1 is really big. If I told you, give me a number close to 2, you wouldn't say 3 or 1. You'll say like 2.01 or 1.99. But to make numbers work nicely, we're going to choose a 1 and we're going to solve this. Add 2 to each side. So x is between 1 and 3. Remember what I want. I want this to be smaller. So I want what I'm going to put on the right to be bigger. What's the biggest this could ever be? If I put a 1 in there, isn't that a 5? If I put a 3 in there, wouldn't that be 3, 7? So the biggest x plus 4 could be is a 3, which equals 3 delta. So what should I do? Well, I'm supposed to choose epsilon over 3, but I chose another value. So every time you do this, every time you choose 2 values, you would say delta equal the smaller of those 2. And then you could say that is 3 times epsilon over 3. Those cancel out. Now, I know I worked it out side by side because we're supposed to, because I wanted to show you that, but in reality, you're really going to work it out straight down. So I'm going to take those and throw them right there. And then you'll say, therefore, the limit as x approaches 2 of x squared plus 2x equal an 8. And that's pretty much it for this section. There's our homework. I added a problem.